Okay, to wrap up this small unit on heteroaromatic compounds, we're going to talk about nucleophilic aromatic substitution. And we're going to abbreviate this NAS. This is much like electrophilic aromatic substitution, where we learned about the Friedel-Crafts, acylation and alkylation and all those, but it's the opposite. Now we're going to have a nucleophile attack the ring, instead of the aromatic ring act as a nucleophile and attack an electrophile. So, electronically it's the opposite, but we're still doing a substitution on an aromatic ring. Now to talk about this, I want to first go back to acid chlorides, and I'm going to draw this acid chloride in kind of a weird way. So if we took an acid chloride and we reacted it with a nucleophile, that nucleophile could attack the carbonyl. We'd make a tetrahedral intermediate, and this O- would push down, kick out a leaving group, and we would have done a net substitution. Note this is not an SN2 reaction. SN2 reactions occur on alkyl halides. Our starting material is an acid chloride. It's not an alkyl halide. It's not an sp3 hybridized carbon. It's sp2. So we go through this different process. Starts with an addition and ends with an elimination to reform our double bond. Okay, so we've seen all of this before, and whether it feels familiar or not, we've definitely seen it. So try to draw a parallel between the reaction I just drew and the reaction I'm going to show now. What if we had kind of the similar setup where we have a chlorine next to a double bond? Instead of being a CO double bond, it's a CN double bond. So now our nucleophile could attack. We push the electron density up on nitrogen. This is kind of like our tetrahedral intermediate. And then this N- can kick back down, kick out the chloride. We've done exactly the same type of reaction. We've done a substitution. We broke a pi bond, so we did an addition. And to get the pi bond back, because we want to restore aromaticity, we had to do an elimination. It's the exact same thing as acid chloride chemistry, except for we have a carbon-nitrogen double bond instead of a carbon-oxygen double bond. Sometimes people call this the carbonyl analogy. We draw parallels between how carbonyls react and then see how nitrogen-containing compounds react. This reaction is not as easy. We do have to disrupt the aromaticity, so this is not aromatic. So it's a little more uphill, so it's not going to be as fast as the top reaction. Nucleophilic aromatic substitutions are oftentimes slow. How do you get around that? Well, often you heat them up. So let's see an example of this reaction. You'd see these, first of all, you see them very often with pyridines, and especially chloropyridines. And then maybe you'll cook this up with an amine. Amines are particularly good nucleophiles for this. So we might heat this up, and what happens is the nitrogen of the amine will attack, kick out the, and we'll end up losing the chloride and losing HCl overall, and we'll get this kind of structure. So this is a nucleophilic aromatic substitution. It works great on making different substituents around pyridines. And it turns out those are sort of in-demand compounds, so this is pretty commonly encountered chemistry if you go into the chemical literature.